Hello everyone! So I wanted to talk through what you're going to be doing today and give you some tips on the lab that you're going to be doing so that it goes very smoothly and you can get to the board meeting and walk out of there with a good understanding of the relationship between radial net force, so that net force towards the center of the circle, and the tangential velocity. So these slides are on Canvas if you want to look through them yourself. So when I say tangential velocity, let's talk about that. What I mean is the velocity that is tangent to the circle that the object is moving on. So that basically just means the speed of the object and the velocity, the direction of it. And that tangential velocity will always be 90 degrees from where a line drawn from the object to along the radius. So it'll always be kind of along that circle, but won't ever curve. So the tangential velocity is a straight line. It's the velocity for a moment when the object is at that point around the circle. And so it is a constant speed. So that is kind of helpful for our purposes today. Why don't you open up to pages 4 and 5 of your packet and just make sure you write down which mass you're supposed to be using. So 20 grams, 50 grams, 100 grams, or 200 grams based on the table number that you sit at. And you're going to need to convert those masses to kilograms because in physics we always are going to use kilograms. So reminder, there's 1,000 grams in every kilogram. I'm going to go over this in just a second, but make sure you keep the radius at D, which will make sense in just a moment when I show you the lab. And then before we actually get going on this lab, I want you to think and be thinking as you're watching this how you are going to calculate the tangential speed. So there's a column for tangential velocity, and you're going to need to calculate that. So you're going to need distance and time, but since we're going in a circle, think about what that circular distance is and think about what that time is. Okay, so here is our lab on Pivot. I assigned this to you. The codes are on Canvas under important course information if for some reason you weren't here the day that we did that. So this is what you're going to see. You're going to want to hit this little caret and choose whichever mass you're supposed to be using. And then you're going to want to choose the speed. So these speeds, because there's 8 or 5, you're going to want to split those tangential speeds up in your group. So everyone should do 2, but you shouldn't all just do the same 2. So you want to split those up, so maybe one person does tangential speed 1 and 2, the other person does 3 and 4, and the next person does 5 and 6, and so on and so on. So when I said keep the radius at D, this is what I mean. Make sure you click that. And then you'll just click whatever speed you need to use. And then you have to hit go every time you change any of that parameters that you're setting, because otherwise you'll just see the same scenario again, and you'll get the same data again. And that's not what we want. We want to be as efficient as possible today. So you're going to hit your little toolbox in the upper right-hand corner, turn on the clock and the ruler. First thing you can do is measure that radius. So it is, this is pretty straight. You can tell that it's straight because the pulley looks like a circle. It's not on an angle at all. Okay, so the radius is about 30 centimeters. I can tell because this is where the axis is rotating, and my mass is right about at that 30 centimeter mark. Now this is where I'm going to want to reset my clock. And that's because I want to measure the time it takes to go around once. So 1 rotation, so I want to stop the time when my mass is back where it was. So I'm going to stop it before it actually gets there, and then just use this in time to get it a little bit closer so I have a little bit more control over it. And then I'll use the frame advancer, this little it looks like a fast forward button, but really it's like a slow fast forward, until it's pretty much back where it started. So right about there. And there I can read my time. So it took 3.9417 seconds. Make sure that you reset your time before you want to start recording. So otherwise it'll measure the time from the very beginning and you're going to get a huge time. So be careful to reset it. You're going to record your data, and again, you'll have to change your speed and then hit go, keeping that radius at D, keeping the mass at 50. You'll advance it to where it's starting, reset the clock, go again until it's back where it started, read the time, and then you've got it. So once you put in all of those, once you get your data points in your group, you're going to put all of those data points into graphical analysis, and you are going to graph FNET-R on the y-axis and velocity on the x-axis. And then, and you can measure FNET-R by looking at this spring scale in the video. So this is going to tell me that for this particular example, I had a net force that was radially inward of about, it looks like each one of these, so this would be, that other black line would be 0.1. So this must be 0.02, 0.04, 0.06, 0.08. So it's like 0.07. Looks like each one of those is worth 0.02 for that spring scale. Not all the spring scales will be the same. So that's how you're going to measure FNET-R for your particular tangential speed. You'll calculate that tangential velocity, take all your data points for your group, put them into graphical analysis. Make sure that everybody has that graphical analysis file, because I want everyone to practice linearizing and everyone to practice writing that physics equation. So make sure that your physics equation has physics variables in for y and x. Please start with y equals mx plus b. Make sure your slope has units, so your slope number has units. And make sure that your y-intercept also has units. So be really careful with writing that physics equation. Start with y equals mx plus b. If that's going to help you be successful, then you should do that every single time. And most of us still need that support to write a physics equation based on a graph. Then when you go into that board meeting, you're going to want to answer some questions that I have printed for you. You're going to want to have someone be a recorder on the board. You're going to want to put the masses together and try to figure out what that relationship is between FNET and velocity.